Alright gang, here we go. So this is Chem 1, Unit 3, Chapter 5, Part 2. We're going to be talking about periodic trends. In the last video, we talked about the periodic table. We talked about Mendeleev and how he organized the periodic table and other scientists. We talked about the groups of the periodic table, so on and so forth. And remember that organizing the periodic table by mass is what Mendeleev did, and now we do it by atomic number. And then he also grouped them by chemical properties. And they had these certain patterns that appeared, remember? So we're going to specifically talk about specific patterns that appear across the whole periodic table, and these are referred to as periodic trends. Okay, and we're going to be talking about four big ones. All right, the first one we're going to talk about is called Z effective. Now it's the most important of the four. So this is the granddaddy. This is the one that we're going to refer to over and over and over again throughout this whole video and later videos. So make sure you really understand this first one. All right. So before we jump into the definition here, I just want to take a moment just to talk about something real quick. So this guy here, so let's pretend we have an atom. So in here we have a nucleus, and in our nucleus we have a bunch of positive charges. It doesn't really matter how many we have. We just got positive charges because it's the nucleus. There are possibly neutrons in there, but they don't have a charge, so we don't really care about those right now. All right, so we got those, and then we've got electrons that are surrounding our nucleus, right? So we've got, we'll just do a simple Bohr model of an atom here. It doesn't really matter. And we know that they don't actually follow these kind of patterns, whatever. But the electrons are going to be surrounding and, orbiting, if you will, the electron, right? We've already talked about how that's not really how electrons behave, but, it's an easy enough way to think about it for this, what we're talking about today. All right. So if you know that electrons are negatively charged and protons are positively charged, and you also are familiar with the idea that opposites attract, that if we have a positively charged something and a negatively charged something, they're going to be attracted towards one another. If there's two positives or two negatives, they're next to each other, they're going to be pushed away from each other, right? So you can kind of think about this interaction between the protons and the electrons as kind of magnets that are interacting with each other, right? If you put the north and the south pole together, they'll be attracted to one another. If you try to put two south poles or two north poles together, they're going to be repulsed. All right, so they'll be pushed away from one another. So that's kind of what we're after in this thing here. So these these electrons that are around the outside, you should already be familiar with the outside electrons are referred to as valence electrons. Okay, and so these valence electrons, and all the electrons, they're getting pulled at by the nucleus, right? They're negatively charged. The nucleus is positively charged. These electrons are going to get pulled towards the nucleus, right? They're getting pulled in towards the nucleus. However, think about it. The ones that are on the inside here, think about these guys here. So they're around these inside ring ones. They feel the full force of the nucleus, right? The nucleus will pull on these guys, and the electrons will be pulled inside of them. But then think about the valence electrons here. These valence electrons, they're going to get pulled in towards the nucleus. However, between them and the nucleus are these other electrons, right? And both of these electrons, the valence electrons and these inner electrons, are both negatively charged. And so these negatively charged electrons are going to be pushing back against the valence electrons. So the valence electrons are going to be pulled towards the nucleus by the positively charged nucleus, but they're also going to be repulsed by the inner electrons, the electrons that are between it and the nucleus. So we call these inner electrons, because they're blocking or shielding the nucleus's effect, we call these guys shielding electrons. Okay, shielding electrons. So these guys are valence electrons, and they're on the outside, and then these guys are shielding electrons, and they're the ones that are in the middle. Okay, so what this periodic trend that we're about to talk about is called the effective nuclear charge, and essentially it's the effect that the nuclear charge has on the valence electrons. All right, so the effective nuclear charge, all right, is the effect the nucleus has on valence electrons. All right, so whenever I ask you what's the effective nuclear charge, it's the effect the nucleus has on valence electrons. All right. So when we talk about effective nuclear charge, all right, it's the net positive attraction the electron feels from the nucleus. Okay, so and specifically, it's not just the electron; it's specifically the valence electron. All right, so it's the the effect these valence electrons feel from the nucleus. Okay, so electrons that are farther away from the nucleus feels less attraction, right, than the ones that are close. Just the same idea as a magnet. Remember, we could talk about this in terms of a magnet, right? The nucleus is positively charged, the electrons are negatively charged. If you take two magnets and stick them close to one another, you're going to be pulled closer together. That magnetic force is pulling your hands, those two magnets together. Same thing happens with the protons and electrons. When these electrons get close to the protons, they're going to be pulled closer to the nucleus. If you pull those two magnets far apart from one another, there's not going to be as much magnetic force pulling them together. The closer they get, the more force you get, right? Okay, so the farther away they are, the less effect there is, and if there happens to be more shielding electrons, they get less effect from that as well, because they're blocking the effect of the nucleus. Okay, so in general, this formula here is what we can use to calculate the effective nuclear charge. All right, so Z effective, remember we talked about previous videos, several units ago now, we talked about how Z represents the number of protons. Okay, so Z is the number of protons, and we subtract out the number of shielding electrons. That's the S value, the number of shielding electrons, or the number of inner electrons. All right, so let's do a couple here real quick. So if we talk about, let's do magnesium. All right, so magnesium, the Z effective for magnesium, well, pull up your periodic table, you find magnesium, its Z is 12 because that's its atomic number, and then we subtract out the shielding electrons. Now, the trick to finding the shielding electrons is you're going to go to the row above it and find the noble gas in the row above it. So magnesium's on row 3, the noble gas in row 2 is neon, and neon has 10 electrons, so we'll put 10. So then we get 12 minus 10, and we get 2. So the Z effective for magnesium is 2. All right, and then we can find, let's see, let's do another one. Oh, how about silicon, right? So silicon, the Z effective for silicon, well, silicon is 14, so the atomic number is 14. We're going to subtract out the shielding electrons, so above it is neon again, so that's 10, so 14 minus 10 gives us 4. So the Z effective for silicon is 4. All right, so we can see, and you could just kind of imagine, now that you've done enough, you can kind of see, as long as you stay in the same row, your numbers are just going to increase by 1 as you go from left to right. Okay, so as you go from left to right, your Z effective goes up, right? Your sodium is 1, your magnesium would be 2, we just calculated, your aluminum would be 3, silicon's 4, phosphorus is 5, etc., etc. Okay, so as you go left to right, your Z effective goes up. Now let's talk about what happens when we jump to a different row. So let's do the guy that's right underneath calcium, okay, or right underneath magnesium, calcium. So calcium Z effective, so we do the Z effective for calcium. All right, so calcium is 20, its atomic number is 20, and so and then it's shielding electrons, so we go up to the row above it, which is row 3. We go over the noble gases, argon, so it's 18, so we go 20 minus 18, so the Z effective for calcium is 2. Now notice that calcium and magnesium then would have the same exact Z effective. Now that's not actually true. Z effective actually decreases as you go down farther because there's more shielding electrons, right? Because as you go down farther, you're adding on rows. So you're, number one, you're getting farther away from the nucleus, and you're adding on more shielding electrons. So as you go down, your effective nuclear charge actually drops. Okay, so this formula only works for the rows. It doesn't work for columns. Okay, so if you're calculating Z effective, it only works for your rows. Okay, this formula does. Okay, so let's jump to this periodic table here. Now at the bottom of part 2 notes, you've got like a blank periodic table that looks very similar to this, and we're going to be drawing different trends. So here we go. So Z effective, now we already said Z effective increases as we go left to right. So we're going to draw an arrow from left to right showing that Z effective increases as we go this way. All right. So Z effective increases as we go left to right. And then Z effective also increases as we go bottom to top. All right. Bottom to top. Because as we get closer to the nucleus, our nucleus can have more of a charge. All right. So based on this, we can predict which element should have the highest effective nuclear charge and which element should have the lowest nuclear charge. So the highest would be the one all the way to the right and all the way up. So that would be this guy here, which is helium. Now I want you to draw a line right there, and then we're going to write in Z effective right there to represent the fact that it's helium. Helium has the highest Z effective of all the elements, all right? So the lowest would be the one in the bottom left, so that would be francium down here, all right? And we won't record that. We're just recording. So make a note on your notes maybe that arrows indicate the increasing whatever it is that they're talking about, and that we're labeling the highest of those elements, all right? Okay. So this next guy we're talking about is atomic radius. Okay, atomic radius is defined as half the distance between the nuclei of two atoms of the same element that are bonded together. So essentially you've got two atoms, right? You've got one nucleus, you got another nucleus, and they're bonded together, meaning they're sharing electrons, right? So they're just kind of whatever, their electrons are bonded and they're sharing their electrons. Okay, and so this distance between them from here to here, that's the distance between these two nucleuses. And so we're talking about half the distance between that. That would be defined as the radius, half that distance. Okay, all right, so you got your nucleus 1, okay, and your distance nucleus 1, nucleus, the same thing. All right, so anyway, so you got this guy and you're talking about half the distance between those two. So that's atomic radius. All right, so think about what happens in terms of Z effective. So if you have your atomic radius, so we're just talking about how far away are the valence electrons. And remember, Z effective is how much the nucleus is able to affect the electrons on the valence, the outside electrons. So the electrons that are farthest away, if they're far away, that means your Z effective is not as effective, right? If your Z effective is really high, that's essentially like having a really strong magnet inside your atom, right? So your Z effective has got a really strong magnet. So you got these electrons on the outside. If your magnet is really strong, it's going to pull on those electrons really hard, and so the electrons are going to be dragged in closer. If your Z effective is very low, that means your electrons aren't going to be pulled as hard, and so they're going to be able to be farther away. So essentially, your Z effective determines what your atomic radius is. So if you know your Z effective is really high, you know you're going to have a very small atom. If your Z effective is really low, you're going to have a very big atom. So essentially, it's just opposite of whatever your nuclear charge is, okay? Atomic size, so these reasonings here are very important. This is the kind of thing, this is really what I want you to know. You need to know the trends, but I really want you to know the reasoning behind it. Okay, so atomic size increases as you go down a group, because as you go down there are more energy levels, right? You're going down, you're adding more levels to it, therefore you're increasing your radius, all right? Your atomic size, though, decreases as you go across a period from left to right, right? We should left to right. And so it decreases as we go left to right because there's an increase in the nuclear charge, in the effective nuclear charge. All right, in the effective nuclear charge, and therefore the nucleus is pulling harder on those outside electrons, making the atom smaller. All right, so if we're going to jump back to our periodic table, we've started back here, and we want to be able to label these guys as well. So let's choose a new color. What color should we choose? Ooh, how about purple? So we'll do purple. So our atomic radius, remember, is opposite of our Z effective. So that means when our atomic radius is going up, our atomic radius is going down. So the atomic radius is going to increase as we go right to left. Okay, so the atomic radius increases as we go right to left. And then the atomic radius increases as we go top to bottom. Okay, so the atomic radius increases as we go this way. Now, so based on this trend, which element would have to have the biggest atomic radius? Well, the biggest one would have to be here in the bottom left, right? The most to the left and most bottom. So that would have to be francium right here. So we'll put in atomic radius. Now, for those of you keeping score at home, atomic radius, cesium is actually bigger than francium, which is kind of an interesting thing, and it's all because of where these F block comes in, all right? But for our class, we're just going to assume that bottom left is always the biggest. It's the biggest atomic radius, all right? If you're curious as to why cesium is actually bigger than francium, then maybe you should take Chem 2, all right? All right, so that's atomic radius. Next guy up is ionization energy. Okay, ionization energy is defined as the energy required to remove an electron from an atom. Okay, so these nucleuses have electrons that are orbiting them, and if we want to take away an electron from one of them, we have to give energy in, right? You imagine somebody holding on to something, okay? If they're holding on to it and you want to take it from them, you have to put in more energy than they're currently using to hold it, right? The nucleus is putting in energy to hold it, so in order to convince it to give up an electron, you have to put in a certain amount of energy to rip that electron off. And that value, that magnitude of energy, is defined as the ionization energy. Okay, so imagine this. Once again, we're going to go back to Z effective. So if your Z effective is really, really high, that means that atom is holding on. It's a very strong magnet. If you've ever played around with really strong magnets, you know that when two really strong magnets are stuck together, it's really hard to get them apart. So the stronger those two magnets are, right, the harder it is to get it off, the more energy it requires. So if your Z effective is really, really high, that essentially means that your that's stuck, right? That electron is stuck in there, and the Z effective is holding it in place. So in order to remove that electron, you need to put in more energy than the Z effective is currently putting in. So if your Z effective is really high, that means your ionization energy is also really high. Okay, so your ionization energy decreases as you go down a group, because you're adding more energy levels, so there's more shielding electrons, so the nucleus doesn't have as much of an effect. So it's easier to pull them off. So the shielding effect is blocking the nuclear charge, and it's easier to pull those guys off. All right. And then finally, your ionization energy increases as you go across a period, because there's more and more of a nuclear charge. Your nuclear charge goes up, and so therefore it's harder and harder to pull an electron off. Okay, so once again, notice how we specifically went back to effective nuclear charge and the shielding effect in order to talk about ionization energy. So let's draw this guy on our periodic trends as well. All right, what color should we choose? How about, oh, I'm feeling like a nice, like blue would be cool. So ionization energy follows the same trend as Z effective. All right, so because our Z effective goes up, our ionization energy goes up. So we'll draw that, and then, so therefore, it's also going to do the same thing over here. Because I'm running out of room, I'm going to write it like this, and I'll put my arrow right next to my Z effective. It's really hard to draw straight up and down lines on this tablet. Anyway, so ionization energy goes up and down like so. Ionization energy increases left to right like so. All right, last one, okay, is the electronegativity. And this is the ability of an atom to attract additional electrons. Okay, now essentially all atoms want, okay, to be like their nearest noble gas. Okay, so like the halogens, remember that's group 7A, only need one more electron to be like the nearest noble gas. So that's why they're so reactive. The alkali metals only need to lose one more electron, so they only need then that's why they're so reactive, because they're able to give up their electron really easy, whereas the noble gases or the halogens are able to attract an electron really easy, because they're only one electron away from being like their nearest noble gas. All right, so essentially electronegativity is like a measure of how much energy the electron is able to or the atom in question is able to spend in order to buy another electron, more or less. Okay. So electronegativity decreases as you go down a group. So Z effective, is decreasing as you go down a group as well, right? So think about that strong magnet. If you have a really, really strong magnet and you put another magnet on it, there's still probably pull left. That magnet could grab onto another magnet, right? But if you have a really, really weak magnet and then you try to put another magnet on it, then that second magnet that gets stuck isn't going to be stuck as well, right? So it's kind of that idea. It doesn't quite hold up as well with the magnet analogy, but you can kind of imagine how that might work. All right, so electronegativity decreases as you go down a group and increases as you go across a period. So it essentially follows the exact same pattern as Z effective. Now, with one caveat here, noble gases, because remember we just said all atoms want to be like their nearest noble gas. Okay, now noble gases are already a noble gas. Okay, so they don't want any more electrons. So noble gases have an electronegativity value of 0 because they have no ability to grab another electron, because that's it. That's all they have for them. Oops, wrong way. All right. So let's draw electron. Ooh, we forgot the ionization energy. So ionization energy, highest element here for ionization energy would be up here with helium. All right, so we'll put ionization energy there. All right, now we have one more. We have the electronegativity, which we just talked about. What color we should do a green? We haven't done green. All right. So electronegativity follows the same trend as Z effective. So we'll put, oh no, I'm too close to the bottom, electronegativity. Oh my goodness. All right, maybe we'll do it. We'll do this, electronegativity. So electronegativity goes from left to right, like so. Okay, and then electronegativity goes bottom to top, like so. So that's electronegativity. Now, which one has the highest electronegativity, do you think? Well, the highest electronegativity would have to be the one in the top right corner, right? So you might be tempted to say helium, but wait, we said noble gases have an electronegativity value of 0. All right, so therefore it can't be helium. Right? Helium's got an electronegativity value of 0 because it's a noble gas. So it has to be the most top right non-noble gas, which is fluorine. All right, so this guy here has to have our electronegativity. All right, so here's your periodic table that kind of guides you. I really highly recommend watching this video again or doing the practice problems, coming to ask for help. This stuff is tricky, and it can, like, there's lots of things to consider, and it's also really tricky because you've never really seen an atom. We deal with them all the time, but we deal with millions and millions of them at a time. Okay, so you really got to be careful when you're working with these and thinking about what's going on. And it's really quite tricky. So make sure you do lots of practice problems, ask questions when you get them, and and just keep on keeping on. All right, let me know if you have any questions.